Okay, hello everyone. I've been wanting to do this presentation for some time now, and it deals with the limitations of large diameter hose as supply hose in our firefighting operations. So, as the former chief of the Fire Bureau, I was in charge of fire investigations and inspections, and oftentimes we would get complaints after a fire that there was not enough water pressure or there was not enough water available for firefighting. So during our investigation, we would have to look at a couple of things. So one thing was, what is the water availability in the area of the fire? So as the chief of the bureau, I would send my inspectors out and they would do a fire flow test. And if they came back with results of the fire flow test that showed there was adequate water pressure, then we would have to look at other issues that would have impacted the firefighting operation. And oftentimes it was the tactics used that were not adaptive to the water main system. And what I mean by that is, at least in my area, the way we do business is a fire company will lay a supply line from a hydrant to the fire and attach to the attack pumper. So the issues are, is there enough pressure in the system to get the water from the hydrant, the water mains, up to the fire scene? In often cases, it's an issue of what we call unsupported operations. So the water is limited, the GPM is limited based on the pressure in the water main system and the friction loss in the 5-inch supply hose. So when we did our fire flow testing, we used a CAN program. So we documented the flows, and we would come up with a fire flow availability. And we could use this to document the hydrants in the area. So in this map, we're able to identify this section of water main was available for a flow of 2,500 plus GPM. So that said, there was adequate water in the water main. So something else had to be the issue with why the attack pumper wasn't getting enough water at the fire scene. So looking at large diameter hose, right? Some facts and characteristics. We have we also have limitations of large diameter hose. We're going to talk about unsupported use of large diameter hose in supply operations. So some of the characteristics. Large diameter hose is used for water supply. So in the picture to the left, we could say that the hose was dropped at a hydrant, laid to the fire scene, hydrant was turned on, and we got water going up to the fire scene. Other issues that I found when I looked into the large diameter hose characteristics is currently NFPA has a test pressure of 200 psi. Formerly, the older large diameter hose was tested to a pressure of 185 psi. So again, you need to know your equipment, what age your hose is, what the test pressures are, what you can, how much pressure you can put into your hose, keep it under the test pressure. So the other issue with the large diameter hose is we talk about hose coefficients and figuring out friction loss. And I'll go over that in a second. And then I was looking at the new 5-inch hose in my firehouse, and the snap tight hose, it's service tested to 225 pounds. So there's definitely an increase from the older 185 psi hose test pressure to current day standards. And again, I'm going to show it in a second, but when we talk about friction loss in fire hose, we have to look at the coefficients from the manufacturer. So this is just an illustration of primarily how my department would do business. We would lay a 5-inch hose from a hydrant to the fire scene, right? And we're depending on the pressure in the water main system to push the water through the hose up to the attack pumper. And that oftentimes was the issue. Going back to the water main systems, the American Water Works Association recommends a residual pressure of 20 psi on the water supply system. This is also a minimum pressure that's regulated in my area by the New Jersey Bureau of Public Utilities. Reason being is they want that residual pressure high on the water main system to keep out any infiltration of groundwater into that water main system and cause contamination. Because remember, the same water mains that we use for firefighting is the same water mains that we use, for drinking and everything else in domestic use. So when I talked to my water purveyor, I said, "What kind of pressures do you have on the system?" And they told us they normally have a pressure between 50 and 75 psi as a standard on their system. All depends on what part of the town you live in. So that is the pressure that is available to push the water through the 5-inch hose up to the scene to our attack pumper. So we have to look at friction loss calculations. So NFPA ISTA gives us a friction loss formula. And that friction loss formula is the friction loss equals the coefficient times the gallons per minute squared times the length of the hose leg. So in this case, we know what the friction loss is, and I'll discuss that in a second. But when we talk about coefficients, if you look at the table from IFSTA and NFPA, this is the table that has been around for years and years and years, and is more likely a average of findings to give us a friction loss coefficient. Now, if we look down here at 5-inch hose, we can see our 5-inch hose friction loss coefficient is 0.08. So that would fill into the coefficient over here. So let me get rid of that. Okay. Stand by for 1 second. All right, so Q. In the fire service, the quantity, the amount of water in gallons per minute when we do these friction loss calculations is illustrated by Q. And Q is the gallons per minute divided by 100. And when we do our friction loss calculation, we take that and we square it. So multiply it by itself, times itself. So in this case, we know what the coefficient is if we're using the standard table, which is 0.08. We know the length of hose. So the length of hose is divided by 100. So if we have 500 feet of hose laid out, we divide that by 100. So L gives us, in this case, 5. Going back to the friction loss chart. So I contacted SnapTight and I looked at the supply hose that I currently use in my fire company, and it's SnapTight HFX. So I called them up and they sent me a coefficient, chart coefficients, and you can see all the coefficients for SnapTight's hose is 0.04. So big drop from the 0.08 standard table from NFPA and ISTA. So in this illustration, all right, we're looking at situation where the apparatus is laying a 5-inch supply line from a hydrant. And the static pressure on the water main system, in this case, static pressure is 50 psi. Let's see if I can get that. All right, so 50 psi is my static pressure on my system. All right. Now, I wasn't able to keep, I need to have 20 psi on my compound gauge. That's pretty much standard the way we teach our pump operators. So if I need to keep 20 psi on my compound gauge, I need to subtract 20 from 50. So that only leaves me with 30 psi to push the water through the 5-inch hose. So I already know my friction loss formula. I know that I already have my friction loss is already 30. That's available, right? I know my coefficient. I know the length of the hose divided by 100 is 5. The only thing I don't know is my Q squared. So that's what I'm trying to find. I need to find that gallons a minute available based on the length of the 5-inch hose lay and the friction loss the pounds per square inch pressure that's available to overcome that friction loss. So if I go through my calculation, I know my friction loss, I know my coefficient. I don't know my quantity squared, and I know the length. So if I get rid of the 5 by doing algebra, again, whoever thought we'd be using algebra once we get out of school. So I need to get rid of the numbers to get to my Q squared. So if I take 5 and I divide 5 into 30, I end up with 6, right? So now I need to get rid of the 0.08. So if I divide 0.08 by 0.08, I get 0. And if I divide 0.08 into 6, I get 75 GPM is my Q squared. So now I have to work backwards to find out what Q is. So to find Q, I take my 75 GPM. Right? Now I take the square root of 75, which gives me 8.6. So 8.6 would be Q squared. So in the beginning, in order to get Q, I divided the gallons per minute by 100. So now I have to multiply this, to multiply Q, 8.6 by 100, and it gives me 860 gallons per minute, roughly. All right, that's a good estimation based on what I know as far as the pressures and using that 0.08 friction loss coefficient. So in this case, my water available at the pump would be 860 gallons per minute. That's based on 30 psi of pressure pushing the water through the 5-inch hose into the pump. And again, I could be as long as I have the water in the system, I'm good. However, I'm not going to get much more than that because I'm limited by the static pressure and then the friction loss. So what I want to do here is just to show you and compare the examples. I'm going to use my 0.04 coefficient that I was given by Snap Tight Hose to do the same example. So in order to get my Q squared, I come up with 12.2. I need to multiply it by 100, and then I come up with new gallons per minute of approximately 1,220 GPM. So a big difference, almost a 30% increase over my previous example. And that's based on the newer hose and the lower hose coefficients. So here's a real life example. And in this case, I use the 0.08. So the engine company came in, they dropped the line at this hydrant, 600 feet to the fire, and it was an issue. We didn't have enough water. When we went back and did the fire flow test, we found that there was plenty of water out here on the highway, out there on the highway, and it was an issue of the pressure in the water main system and the length of hose lay and the friction loss limited them to having that water available. So some important takeaways, right? Have an understanding of your water supply system. Okay, realize the limitations of your large diameter hose when used unsupported. Right? And if you're looking for big flows, you're going to need to put the engine on the hydrant and supply back to the scene. So in this case, here's an illustration of our engine. Engine is hooked to the hydrant. Right? We could also trim out this hydrant with a 2.5 inch valve to get more water, but we're going to get the more water through the system because we're getting the maximum water from the hydrant in this case. But some limitations: the water available in the supply system. If the water main is only capable of supplying 1,500 gallons a minute, you're not going to get more than 1,500 gallons a minute or a little less. You're limited to whatever the water system has available, right? Again, we're limited to the service pressure of the large diameter hose and the overall length of the hose lay and the supply engine pump rating. So if I have a 1,000 GPM pumper on this hydrant, I'm probably not going to get much more than 1,000 GPM. Versus if I put a 2,000 GPM pumper on the hydrant and I had the water available, I could supply more water. All right, so that was just a quick overview of some of the limitations of large diameter supply lines when they're used unsupported, and just some of the math that you can use to figure out some different hose computations based on the friction loss formula. Just doing what you call a reverse friction loss formula. Since you know the friction loss, you just need to calculate the quantity. So I hope you enjoy this, and I'm going to try to put up some more videos in the future. Thank you.